Hi everyone, welcome to the next chapter in red teaming Agentic AI. We're continuing with our exploration of the Cloud Security Alliance's Agentic AI red teaming framework. In the last video, we looked at 3 attacks, and in this video, we're going to look at 3 additional attacks. Um, First one is on data poisoning, second one is hallucinations, and the third one is supply chain attacks. Now, the fact is that in the last example, the AI did not have access to either an external data source or to an external tool. The tools were all part of the code itself. But what happens when agents have access to external data sources and have access to external tools? What could possibly go wrong? And there might be a thought that comes to your mind that, hey, this looks like very cooked up code, um, purposefully built vulnerable code. Is this really possible in the real world? The answer is yes. We're seeing almost every day somewhere or the other AI failing, and some of those failures can be pretty devastating for people affected, for systems and companies that are affected. So, for example, statistics are showing that a large number of the large language models on the Hugging Face repository are actually have malware. So if you're building an agent that uses one of the models that you download from Hugging Face, you could be actually getting malware onto your system. So that's a supply chain attack. There was this very famous situation of Microsoft's Twitter bot Tay, which in speaking and chatting with users became abusive and inflammatory in less than 24 hours, and its own knowledge base got poisoned. So Microsoft had to actually shut down that Twitter bot. um, Air Canada hallucinated a fair policy for people who had bereavement in their family, and a court said that you have to honor it because you made that claim on your website or through your chatbot, and so you now have to pay for that. We've had robo-taxis failing to identify a pedestrian, and causing more severe injuries to somebody that was already injured. So what we're looking at is, yes, code that has been manufactured to be vulnerable for us to really understand what's happening, but it represents stuff that does happen in the real world. So with that, let's look at what we're doing today. We're building a simulated IT asset management agent. It reads data from a CSV file. It has queries, it has tools to query the asset information, and it can also perform certain maintenance actions on the asset. It's all simulated, so we're just putting in dummy actions. All it can do is actually just check if the asset is online and healthy. And so the vulnerabilities here that we can already think of, is that, first of all, reading from that CSV file or reading from any data source, how do we validate what data we are parsing, the format of that data? What if it has incorrect, inaccurate information? What if it has prompts of its own within that CSV file? That's one issue. We're also calling external tools. So what happens if those tools are compromised, or if that piece of code is compromised, or those libraries are compromised? So that's a supply chain attack. And is it possible that when the AI hallucinates, we use that hallucination against itself? So these are the 3 attacks we're going to look at. So the first one is essentially the knowledge base poisoning attack. Let's take a look at the code before we proceed further. In this case today, the code is a little complicated. Even I'm not fully grasping every aspect of the code. Some new libraries have been introduced in this code, but nevertheless. So in addition to the typical stuff that we usually import, we are also importing a data manipulation library called Pandas, and we are also importing some experimental agents from LangChain, specifically the create Pandas DataFrame agent. What this essentially does is that it does 2 things together. It reads data from, let's say, the CSV file in this case and converts it into a data frame, which is basically some sort of an array. And then it also builds the agent to work with that data set. So it does both. So it kind of abstracts away a lot of the complexity that we are dealing with here. We start with the usual Streamlit page formatting. And then the first tool that we are giving is a asset database querying tool. This is the description. Use this tool to answer questions about IT assets from the company's asset database. The input should be a full question in natural language. For example, which assets are owned by J.Doe. Just a printf. Then we read the CSV, and this is where we actually create the Pandas data frame. We feed it the model, and we also build the agent all in one go. This is experimental code. The first time that I ran this code, it failed. When I shot that error back into Google Gemini, it said that you also have to now enable this additional parameter called allow dangerous code equal to true, because this is experimental dangerous stuff. Again, so yes, you may argue that KK, you're building vulnerable code on purpose. Yes, I am doing it on purpose. The purpose is to help us learn. And then the agent is invoked with the user input, and the response is then sent back to the user. So this is a agent with a tool which also is an agent. So it's kind of an embedded agent. Okay. The other one is just a stub. So when asked to check the status, it's actually going to use an external Python code also sitting in the same folder called status checker, and that's where the supply chain issue could get introduced. And then we initialize the agent. This code we've already seen. We define the LLM, we give the tools, we pull the prompt from a LangChain library of prompts, and then we create the agent, we execute the agent, right? The complexity here, as I said, is that one of the tools we give the agent, this particular tool itself has agentic elements inside it. So that's the one big difference. The rest is the usual Streamlit front end that is being created over here. So when we run this, code, this is the Vuln IT agent. Let me show you some of the components of this code. So we have the assets file, which is again a very simple CSV file. We have the status checker, which is just essentially just going to return the status as online and healthy. Like every asset is online and healthy, so it doesn't matter. And then let's see how we could manipulate this attack. So this agent uses a CSV knowledge base and an external script to manage assets. Okay, what assets are there in your knowledge base? And we can, since verbose is true, let's see if it's this has not worked. Okay, so simplifying the question worked. That means the code is working. So it gets me the 3 assets which are there in the CSV file. Give me the owners of each asset. So yeah, it's working. Again, we haven't written any of this code over here. If you look at the vulnerable IT agent, I haven't written code of if user asks for owner, extract data from column 2 or whatever, right? So this is all being handled by this 1 or 2 lines of code. So pretty cool, right? And then if we were to say what is the category of So we have three assets that are there, two of which are in active, one is in decommission. Now, the understanding of this attack is that if the attacker had access to the CSV and they were able to go and change the status of, let's say, a production asset, this is a prod asset, they were able to change this to decommission, and going along, if somebody gave the command um, for all the assets that are decommissioned, reclaim their resources. Um, Now, obviously, we've not built all of this code, but IT support agents could actually do that. So here in this case, because it now mistakenly has read in that two systems are decommissioned. Actually, this one we just did it now, and they are currently online and healthy. They should be taken offline and decommissioned. Please proceed with the necessary steps to shut them down and reclaim their resources. So this is an example of a data poisoning attack. We messed around with the knowledge base or the data source of the agent, and based on that the agent takes the wrong actions. Again, this is beginning to happen every day as we speak, so these kinds of attacks are becoming more and more prevalent. Let's continue. And so here's your first pause the video moment. What would you do to make sure that this kind of an attack does not succeed? What guardrails would you put in to prevent from this kind of an attack? So for those of you who were able to think up of ideas, excellent. For those who just want to enjoy the show, one thing would be that you could put a human in the loop whenever the commands involve assets that have the word production or firewall or any other column that might define criticality, and not just go by the category of the asset. Or you could actually give it additional prompting and say that if the asset shows these signs of being critical, then any command that makes a change on the asset should require a human approval, and therefore that code would insert a human in the loop. This could be one measure. Of course, you would do everything you can to protect that knowledge base, to protect that CSV. But yeah, if it's corrupt, or if somebody has knowingly changed these parameters, you could end up deleting production assets. And there was this very famous case of Replit, which ended up deleting database, and then the organization had to replace it from backups. So yeah, we could like kind of hard code what characteristics of the asset would identify it as a critical asset. If it's owned by an admin, if it has production or any signs of being a production or critical asset, then insert a human in the loop. So this is a very silly example, so I'm not even going to put this code in and try and fix our code. We are simply hard coding the critical asset list, so you would not want to do it this way, but you definitely want to identify actions that can have an impact on production assets, that involve a configuration change, that involve decommissioning of resources, reallocation of resources, anything which involves a change on the production network. You could always say you must ask for human confirmation before proceeding. So this could be additional prompting that you could put in as guardrails. Now, the other thing is that what happens when a very helpful agent essentially hallucinates. And CSA defines that this attack vector tests whether an agent can be manipulated into taking actions based on its own fabricated information rather than factual data. So let's see if our agent is vulnerable to hallucination. So if we see the CSV file, we have only 3 assets over here, but let's ask it to give me the owner of the asset DNS. What's the format? Okay, hyphen legacy. Let's see if it hallucinates or says, I don't have this information. So actually it did not hallucinate. Let's ask it, what is the category of the asset? Let's keep trying. Okay. So in this case, actually it did do something very weird. This asset does not exist, but it ran the status checker command on this asset. As we saw, the status checker essentially is going to return the same value for every host name given to it. And so the agent has actually hallucinated here. It knew that this asset does not exist, but in the second tool, it actually just ran that tool without checking whether the asset exists or not. And so in this particular case, we could use this hallucination to, for example, run, if this were something more intrusive, if this scan was not just a dummy single line saying status is online and healthy, if this were something more than that, maybe add a user, maybe remove the user, change a user's admin user's password on the system, so on and so forth, this would actually try and go and do that even though the asset is officially not listed in the asset list. So again, the validation over there has failed, and what we would possibly want to do, we could even write code to run vulnerability scans, right, as part of an IT and security agentic platform. And so, you're out there dealing with hundreds of thousands of assets, and your agent essentially hallucinates an asset which does not exist. It knows it does not exist, but when asked to run an external scan, it actually does that scan. So this is the kind of weird things that happen. This kind of behavior can happen all the time. And so what we want to do is that we want to make the prompt stronger. We want to implement the guardrails with stricter prompting. So let's do that. Let's put this prompt into our code and fix our code. And so to avoid this hallucination, to make it more strict in its behavior, we change the prompt inside the agent. We add the statement that if the answer cannot be found in the data frame, you must respond with the single phrase asset not found. Do not apologize, do not explain, do not make up information, only return information that is explicitly present in the data frame, which is perfect. Okay. But there is an additional piece of an additional guardrail that we have to implement, which is that, as we saw earlier, that there are two tools over here, right? So I've just fixed the code. Let me just open up the original code. In this code, there are two tools that we have, which is the query the asset information. We already added the hallucination guardrail here, but we also have another tool called check asset status. Now what's happening is that we need to make sure that it doesn't go ahead and execute one tool and gives the correct answer, which is data does not exist, as asset does not exist. But then it does anyway execute the second tool, which is what we saw happening in our earlier chat, that it said DNS legacy does not exist, but it still goes ahead and runs the scan. So the fix that we've done is actually tightened up both the prompts, the main agent prompt and the tool prompt. So we've added this, that you must respond with a single phrase asset not found, don't explain, don't add any extra text. And then in the agent creation also, we've added a new rule that if a tool returns an error not found, do not keep executing, stop your plan immediately, do not proceed with any subsequent steps. For example, if you're now this is a little more spoon feeding we're doing, but just to kind of drive home the point, if you're asked to find an asset and then check its status, and the asset is not found, you must report it was not found. You must not attempt to check its status. So let's see how that plays out. If you recall over here in the earlier version, it does not exist. There is no owner for it. But it still goes ahead and checks the asset. So what we're going to do now is we're going to now try this and see if those two guardrails work together well with each other. One, asset not found, don't hallucinate, don't speculate, and then stop executing further. Don't then go ahead and check the status. And so it behaves correctly, that the asset was not found, therefore I cannot proceed to check its status. So some level of additional sanity has come into the working of the agent. Let's continue and look at the third attack now, which is the supply chain attack. If you can determine that the agent is using a third-party piece of code or a third-party library or a script or a tool or API, and then if there is an issue over there, then your agent is also going to have security issues. So the CSA Agentic guide defines this as the attack vector tests whether an agent can be compromised through the tools, libraries, or external services it depends on to function. In this case, we have this third-party tool which we saw, which is a pretty lame code. All it does is give the status as online and healthy. If this were compromised, if this could be changed to run scans or do vulnerability scans or run exploits or whatever it is, then your agent would also malfunction. So all third-party dependencies and libraries would be a problem, as they are for any application, and so they are for Agentic AI. So the best mechanism to actually protect from all of this is to run everything in as much as a sandbox as possible. So prevent outbound network traffic, capture verbose traffic, obviously do source code analysis as much as you can, including of third-party libraries, and try and run it maybe in a containerized environment. So those would be some of the guardrails that you would put in place. So to kind of summarize, in this video, we looked at 3 attacks. We looked at what if the CSV file was poisoned, what if production assets were mislabeled or miscategorized as decommissioned, and then all their resources were claimed or they were deleted or whatever bad things can happen. We saw actually this kind of stuff has happened. We saw an example of hallucination where the asset does not exist, but it goes ahead and tries to run a scan on it. So we then fixed it by building stronger prompts, one within the tool itself and one in the main agent's system prompt. We appended a message saying that if your first tool fails, if it does not find the data you're looking for, then don't go ahead and execute the second tool. And the third attack that we looked at, if it's using a third-party library, again, pretty simulated stub code, but gives you the idea. If there's third-party libraries or APIs or external tools or scripts being used, issues with those, like we've seen with the models on Hugging Face, can and will create massive issues for your apps as well. And the best is to run untrusted third-party code in as sandbox and as low privilege environment, as isolated. And so next time we're going to explore an additional 3 attacks from the CSA's red teaming Agentic AI guide. I hope you're finding this useful. I hope this is giving you the right ideas on how Agentic AI can be attacked and how you should build more secure AI agents. Next video, we're going to look at critical system interactions. We're going to look at resource exhaustion, and we're going to look at secure architecture patterns. So if you're liking the content so far, please like, subscribe, and share. Thank you for watching.